Hey Chem 2, hope everybody's good. This is the sixth video in chapter 16. It's going to be very short and it's going to be based on polyprotic acids. So here we go. So polyprotic acids have the form H2X, and it doesn't matter if X is a monoatomic ion, like for instance sulfur, or if it was a polyatomic ion like the example that we have here, which is for carbonic acid. So these are going to be acids that can donate more than one proton. Okay, so either two, or in the case of phosphate, something that could donate three. But let's take a look at this example. So what we have is the equilibrium between the first acid, the fully protonated neutral version of the acid for carbonic acid. So carbonic acid reacts with water. Okay, it is a weak acid, so only reacts part of the way. So you make some hydrogen carbonate ion, an H3O plus, right? This guy is donating a proton to water, so this is the Bronsted-Lowry acid. This is the Bronsted-Lowry base going backwards. H3O minus would take a proton from here, so this guy would be the proton acceptor, so this is the base going backwards, and this would be the acid going backwards. So hydronium ion is always going to be an acid. Okay, so the Ka for this reaction is very small, 10 to the minus 7th. Okay, typical. So this is why when you drink carbonated water, you don't burn your stomach with acid, because the carbonate that's in the water is a very weak acid. So Ka1 is 4.3 times 10 to the minus 7th at 25 degrees. Well, after the first proton falls off or gets pulled off by the water, the second one, to a smaller degree, is also an acid. So it can react with water to donate a second proton, make a second hydronium ion, and make carbonate. Now, once you get to that point, carbonate can't react further because there's no more H's to come off. Okay, so experimentally determine Ka2, the 2 meaning for the second hydrogen to come off. This was the one, the first one coming off. This is the second one coming off. That one has a value of 4.8 times 10 to the minus 11th. You can't calculate these. These are given to you. They're experimentally determined. Okay. The only way you could calculate them is if I gave you the pHs, which I didn't. So let's just assume we just looked those up in a book. Okay. Somebody else did the experiment for us. Well, one of the things you can do is you can always take the two individual reactions and get the overall reaction, right? So let's see what happens to that. And we know what we're supposed to do with equilibrium constants when we add the reactions up. So let's add these two reactions up, and then we'll see what to do with these two equilibrium constants. So if I add these two reactions up, a couple of things that you realize is that on the reactant side, you have two water molecules here. So the carbonic acid isn't going to get canceled with anything on the left. And the water is going to get one water plus the second water is going to make two waters. So let me write all that stuff down, right? Nothing happens to this, meaning it doesn't get canceled out, plus two water molecules. Okay. Now, let's take a look at the hydrogen carbonate. The hydrogen carbonate is formed in the first reaction and then used up in the second. So it's an intermediate when I think about the overall reaction. So just like I could in math, if I make an X over here and then I use up that X on the other side, one X over here and one X over here would cancel out. So those two guys are going to cancel out. It's an intermediate, right? And the coefficient is the same. That's what happens to the H3O plus. You don't see it in the overall reaction because it's formed and then used up. Okay, go over to the other side. This guy's gone, right, because he canceled out with this one over here. So what do I have as the product? I have carbonate and hydronium plus hydronium, which is two hydroniums. So the overall reaction looks like that. Right? The overall reaction looks like just like what you'd expect it to look like. Right? Where in one step, this, I shouldn't say in one step, in one process, the carbonic acid reacts with two water molecules. First one comes in, rips off the first H, makes a hydronium. Second one comes in, rips off the second H, makes a second hydronium. What's left is just carbonate. Okay, when you add the chemical reactions, like we just did, what do I do to those two equilibrium constants? I need to multiply them together. So K, I'll call it capital A for the overall reaction. Right? When you add chemical reactions, you multiply the equilibrium constants is equal to Ka1 times Ka2. If I do the math, K for the overall reaction is going to be 4.3 times 10 to the minus 7th times 4.8 times 10 to the minus 11th. And the overall K is going to be this little teeny tiny number down here. When you multiply those two together, it comes out to 2.06 times 10 to the minus 17th. 11 and 7 is 17, so that's how you get the minus 17. And then 4 times 4, 4.3 times 4.8 comes out to 20.6. That's why this goes down to minus 17th versus minus 18th. Okay? Very small number, very hard to get all the way to the right. That doesn't mean that the first reaction doesn't happen to a significant quantity, but to get 100% of the way, all the way over to the fact where there would only be carbonate would be very difficult to do. It doesn't happen naturally. You're going to have to force it. So K overall then is equal to K1 plus K2, times K2. And another way that you can look at it is the overall equilibrium constant, right, has to come from the overall reaction. So here's the overall reaction right here. So if I write the overall reaction, let's get one more piece of paper. Just turn this one around. Right. So we know the value of the overall equilibrium constant, but what does it represent? Well, it represents the products over the coefficients, the products of the reactants. The coefficients become the exponents. So this 2 here, this 2 becomes, that's 2 squared. And this carbonate is to the first power, because it's to the first power over here, and divided by the products. Well, there's only one, but the reactant's H2. Okay. And that's the first power. The 2 water molecules you leave out because you always leave water out. Okay, so the last thing I want to do is, let me finish up with a note at the bottom of the page, and then I'll draw a picture for you called a distribution diagram. So this is the overall equilibrium constant expression. These are the equilibrium constant expressions for the 2 individual ones. I could just write this times this divided by this for the first one, this times this divided by this for the second one. Okay. And you'd see, if you did all the math, all those things would cancel out in there, and then still get this. Okay. That's for the overall reaction. Overall. Okay. So last note at the bottom of the page. So it's not uncommon, this is very typical, that the second one is going to come off to a much smaller degree than the first one. So let's talk about orders of magnitude, because 4.3 is very similar to 4.8. So they're basically the same number in the front. So 10 to the minus 7th versus 10 to the minus 11th, that's 4 orders of magnitude smaller. That's 10,000 times smaller. That's going to be pretty typical. So what's going to happen is, at very, very low pHs, you're going to have almost completely carbonic acid in solution. It's not going to be able to decompose very much, and I'll show you that in a second by Le Chatelier's principle. Okay. At higher concentrations, at intermediate concentrations, you're going to have mostly hydrogen carbonate in solution. And then at very high concentrations, you're going to have mostly carbonate. So we can follow that with the individual reactions, or probably easier to do it for the overall reaction. So here's the overall reaction. So let's talk about it first from Le Chatelier's principle. Okay. So by Le Chatelier's principle, what would happen if I all of a sudden dumped acid into the solution? Well, then what we'd say is, at a very high pH, where you dumped a lot of acid into the solution, which way would this equilibrium shift? Well, at high pH, it would be there's too much hydronium, there's too much hydronium, get rid of the hydronium. So it would shift back to the left and push this equilibrium that you see right here all the way back to hydrogen, to carbonic acid. That's why if you add, you have seltzer in solution, and you have the pH very low, you won't see any bubbles come out. Okay? As soon as you start to add any base to it, then base is going to raise the pH, and it would be like saying, okay, add extra hydronium ions to the solution. Excuse me, hydroxide ions to the solutions. Well, the hydroxide ions will react with the hydronium ions to neutralize them to make two water molecules. Okay, so hydronium plus hydroxide will make water molecules. So adding hydronium ion, hydroxide ion, and raising the pH is going to do what? It's going to remove hydronium ion from solution. So if you're pulling the hydronium out because you're raising the pH, raise the pH, pull the hydronium out, pull the hydronium out, taking the hydronium away. Which way does this have to shift? It has to shift back in a direction to make more hydronium. So at very high pH, you expect to have a lot of carbonate ion in solution and very little hydrogen carbonate or carbonic acid. So what I'm going to draw now is called a distribution diagram. It's just going to show you the three active species that you can have in solution and where you'd expect to see them. Okay, so here's my beaker down at the bottom here. So if I have some carbonic acid in solution and I'm going to add some acid or add some base, I could try to add acid, see what happens, or later on try to add base. We know base is going to make the pH go up, acid's going to make the pH go down. Okay, so if I add, and my equilibrium is between these three culprits. It's got to be someplace between those guys, right? The difference between them is the amount of hydronium, where this guy has more, this guy has a little less, and this guy has none. Okay, so what you're going to see is way down here at pH 0, which is very possible to get to pH 0, right? That's a hydronium ion concentration of, a hydronium ion concentration of 1 as a pH of 0. So I'm going to see this line here, right, where this represents 100%. This is the percent of each chemical species. So over here, this line is going to be pegged to the top, and it's going to be H2CO3. At low pHs like 0, 1, 2, maybe even 3, I'm going to have almost all H2CO3. I'm not going to have any carbonate or hydrogen carbonate down here. Excuse me. Okay, but what's going to happen is as I start to approach pH 7, this guy is going to drop down. And the HCO3 minus is going to start to become the predominant species. So at intermediate pHs, I'm going to have mostly that intermediate piece. And then when I get to very high pHs, this guy's going to drop down to 0. And my carbonate's going to come up. So this would be mine. Now this is not supposed to be a perfect diagram. These numbers are going to move around a little bit. But if you want to have mostly hydrogen, carbonic acid as the predominant species, lower the pH of the solution by adding a different acid, like a strong acid like HCl. And you can drive this equilibrium. Let me make this a little smaller. Okay. And if I add extra acid to this, I can drive the equilibrium down to all of this stuff, right? So that's what's going to happen. 100% at very low pHs of carbonic acid. At intermediate pHs, around here, you're going to have both the carbonic acid and the hydrogen carbonate. Around 7, the hydrogen carbonate is going to dominate. You're going to have mostly it. The other two species are hardly going to be around. At high pHs, once you get to 9, 10, 11, you're going to have the amount of carbonate in the solution is going to be the most, and the other two are going to start to drop off until you get to the point where you only have carbonate. The two things that never exist together are this guy and this guy, right? They really are on opposite ends of the pH spectrum, whereas the intermediate guy kind of coexists with both of them. Okay, so these places where the numbers are the same are going to be very interesting, and we'll talk about them. That's when the solution is most buffered. Okay, so that being said, that's going to finish this lecture on polyprotic acids, just 15 minutes. And then we're just down to one more for chapter 16, and that's on bases.